Today, I'm going to present our research on optimizing steel structures with reused components using generative design. This work is done in collaboration with my supervisor, Dr. Amin, Hammad, and my colleague, Faraeen, Homayounfard. So in this presentation, I'm going to start by explaining the motivation and background of the research, then followed by the research gaps and objectives. Also, I will explain the proposed framework, as well as what we have done so far for the implementation. At the end, I will share some of the points of the conclusions and the ideas for future work. So in recent decades, population growth and urbanization have brought serious environmental challenges like global warming. One key contributor is the construction sector. This industry alone accounts for about 40% of world solid waste, 50% of global raw material consumption, and about a third of greenhouse gas emissions and global energy usage. As a result, the construction industry has become a key part of global sustainability efforts. One of the key shifts is in sustainable construction is the move towards circular construction. The goal of this is to keep materials in use as long as possible, either by extending a building's life or by reusing and recycling. Between the two options, reuse is more valuable than recycling as it keeps building components intact and gives them a second life. It also saves more energy and reduces embodied carbon since the materials keeps in their original form without further processing. Sorry. So right now, reuse is still not a common practice in architecture, engineering, and construction industry. One main reason is economic uncertainty. Stakeholders often worry that using reused materials could lead to higher cost at the end. Also, the second reason is that the market for these components is not well developed. This means that there aren't enough reliable suppliers and there are no clear standards. Another challenge is access to information. Designers and builders don't have clear or updated data about which reused materials are available, where are they, and do they fit into the design or not. And finally, there are design challenges. It means reused parts often come in different shapes, size, conditions. This makes the design process harder and can limit the creativity and make the process less efficient. So despite the challenges, there are promising efforts being done. A good example of this is the work by Burting and colleagues. They developed a framework for designing truss system using reused components, which helps to minimize both the total weight and material waste. As a case study, they designed a roof truss for the main station in Lausanne using reclaimed parts from electronic pylons, and you can see in the figure. This smart reuse led to 63% reduction in embodied energy compared to using only new components. So, building on the idea of design for use, we can see that existing research has made valuable contributions. However, many of these studies are still limited in scope. They are often focused on just one aspect, such as minimizing material waste, reducing embodied energy, or improving structural connections. What is still missing is something more comprehensive approach that brings everything together, the sustainability, cost efficiency, and effective use of reused components in a single framework. Also, most existing methods rely on traditional optimization techniques, which can make it difficult to explore more complex or flexible design solutions. To address these gaps, this research takes a step further by introducing a generative design-based framework. Unlike traditional methods, generative design allows us to explore a much broader range of options and weigh multiple goals at once. As you can see in this figure, the framework follows a 7-step process to optimize the geometry and topology of steel structures. The main goal is to reduce cutoff waste, cost, energy, and CO2 emissions, all while making sure the structure remains safe and practical. It starts by designing an initial structure using new components. Then these new components are replaced with suitable reused ones selected from a predefined stock. And at each step, different design alternatives are created and evaluated using genetic algorithms. And I will explain the key steps in the following slides. The first step is to define the steel structure. This means setting up the position of the nodes, how the elements are connected, and the boundary conditions such as loads and supports. This gives us a solid, feasible design to start from. The second step, which can be done in parallel, is to prepare the inventory of reusable components. This includes existing steel elements with known properties like their lengths and cross-sections. The inventory acts as a database, following a system to find the best matches for reuse later in optimization process. The third step is to analyzing the structure. This checks how it performs under expected loads and conditions and gives us a solid reference. The fourth is start replacing those new components with reused ones from the inventory. The system looks for reused parts that are at least as long and as strong as the original ones based on their length and cross-section. It chooses the closest match to avoid using more material than necessary. And if no suitable reused part is available, a new one is used instead. Step 5 is evaluating the design by calculating a score that we call it as the R score. This score combines 4 factors of energy, CO2 emissions, cost, and cutoff base. And here you can see how the R score is calculated. All the factors are the summation of the new and reused components. For energy, for new components, we consider the production and transportation. For reuse, we consider the deconstruction, modification, and transportation. And for the total, we sum these two together. Also, for the CO2 emissions, it would be the same in each of these stages. For the cost, we include the production and transportation. For reuse, we include the deconstruction, modification, if needed, and transportation. And finally, the material cutoff phase would be the excessive material that we trimmed because of its longer or larger than what we actually need. Finally, the R score is calculated as the weighted sum of all parameters. Each weight can be adjusted based on what the project values most and specific priorities. The NSGA2 algorithm was used for this optimization. This algorithm begins by generating a population of design alternatives, assigns each one an R score, and evolves them through crossover and mutation. The more sustainable design is with lower R score, it's selected for the next generation to be evolved. The process continues until there is a little improvement across several generations. The final step is to visualizing the design with the highest fitness value. This helps designer clearly see the structure layout along with the cost and environmental impact to have more informed decision making. Now let's go to the implementation. To show how this framework works in practice, we applied it to a case study involving a simple steel structure. We used Grasshopper and Rhino to optimize the topology and geometry of the structure. And we used Karamba for the structural analysis part, which is a plugin in Rhino. Also, we use Galapagos for running the genetic algorithm for the optimization. For the design, we model a 10-meter Warren truss with verticals. There were 5 kilonewton loads applied in lower court, and the height was 2 meters, 3 bays, and also we allowed 0.8 meter for the upper courts. And we also defined 6 different configurations to explore more options. The inventory included the types, quantities, and the length of each cross-section. We used circular hollow section for this case study, and the normal mechanical properties was assumed for each of these elements. For the structure analysis, as I mentioned before, we used assemble model in Karamba, and for the matching, it was all same as I mentioned in the framework. So for calculating the R-score, we do some simplification for our analysis. We assume that modification impacts were negligible, leftover material would be reused, and new components created no extra waste. Finally, we gave equal weight to energy, emissions, cost, and waste. For the optimization, we used Galapagos Solver. We tested two populations of 20 and 50, and the search space included both continuous variables like node positions and discrete choices like topology and component type. The process stopped when the R-score improved under 1% for 5 generations. Finally, we visualized the final optimized truss in Rhino with 13 reused and no new components. We then compared this with the initial design with all new components, and the results were promising. There were 64% reduction in CO2 emissions, 64% in energy consumption, 56% in CO2 emission, and there was around 40% of increase in cost, which we can say that the major environmental benefits can justify the potential increase in costs. In conclusion, this study introduced a generative design framework to support the reuse of steel components in structural design. The results show that reuse can be both environmentally beneficial and economically viable. However, the case study included some simplified assumptions. Future work will focus on improving the R-score, integrating material passports and EPDs, and extending the framework to more complex applications such as 3D truss models. Thank you.